Hello, Lauren.
Hi, Phil.
This is your experiment?
Yep, this is one of my experiments.
One of your experiments. Oh, you've
Indeed.
got a few, right.
I've got a few.
Okay, so you're doing fusion of what into what?
So I'm measuring the fusion of relatively heavy nuclei. So I'm looking at reactions such as oxygen on a lead target, and a sulfur beam on a tungsten target, both of which form the same fused product, which is thorium 220. So that's the mass number. That's the number of protons and neutrons.
Okay, so you're making the same thing but by two different methods.
Yeah, that's right. Two different methods. There's another few reactions as well. So I've got 4 all together that all form the same fused product.
All right.
Yeah.
So what do you get from doing it 4 different ways?
So by forming the same compound nucleus in 4 different ways, we're trying to understand how the nuclei that we put into the reaction affect the products that we see at the end of the reaction. The reason why we want to investigate this is that currently our calculations of how much fused product we expect to see don't actually match with what we're seeing experimentally. And the difference between the experiment and the calculation changes with the ingredients, that is the beam and the target nucleus that we're putting into the reaction.
Right. Do you have a hunch why the calculations in the experiment don't match?
So we have a few ideas, And we think the reason is because we're treating our 2 reacting nuclei as isolated quantum objects, whereas once we have our compound nucleus, we're doing our calculations and treating this compound nucleus like it obeys statistical mechanics.
Right.
And these 2 areas are quite different, and the way in which we get a transition from one to the other isn't really clear to us yet, and it's not being explicitly treated in our calculations.
Right, sounds complicated.
Yeah, it gets complicated pretty quickly.
Yeah, right. So by having different sized things joining to form the same size things, but they don't always stick, is that right?
That's right, they don't always stick.
And so by seeing which ones stick and which ones don't and how often, I guess you get some clues about...
Yeah, that's right. So we're measuring fusion, but what we're actually trying to get at with these measurements is we're trying to determine how much other stuff happens. So it's not just the fusion that we're after, but when these nuclei stick and undergo other reactions and then separate again, we're trying to determine how often that happens instead of fusion.
Ah, I see. Right. Okay. Wow, complicated stuff.
Yeah.
I mean, nuclear fusion that happens in the sun is relatively simple because you're just getting hydrogens combining to form helium, etc.
Yeah.
But when you've got a big thing that can form into lots of different combinations.
Yeah, that's right. So in the sun and the stars, we're thinking about very light nuclei, like you said, like hydrogen and helium. But when we're trying to form new superheavy elements, for example, we're looking at the fusion of very heavy ions with a lot of nucleons, and there's a lot more going on that we need to try and understand before we can create more superheavy elements, for example.
So you're making things heavier than thorium as well?
So I won't be personally in my project, but that is one of the things that we're trying to do here at the ANU. And one of the community's international efforts is to make these new super heavy elements and add things to the periodic table.
Wow.
Yeah.
Okay.
So we're up to element 118 at the moment, organesson. And we've tried getting to 119 and beyond, but there's been very little success so far.
Okay. So what happens in here?
So what happens in here is that we're using this giant solenoid, which is like a giant magnet, to filter out the reaction products that we're interested in, which is fusion, from all the other stuff that might be coming through this chamber.
Okay, so this is at the very end of a beam line.
Yeah, that's right. So our beam comes from the 14UD, which is our accelerator, and it's incident on a target which is present about this here. And then from that target, you get your fusion products, but you also get a lot of other stuff happening.
Shrapnel.
Kind of like shrapnel. And what this magnet is doing is, like I said, it's acting as a filter so that we just get our fusion products landing on our detectors, which are at the other end of the solenoid.
Right, so they sort of curve in the magnetic fields?
Yeah.
Is that right? And big things go over here and light things go there and the exactly right ones land on
Yeah,
your
that's
detector.
right.
Okay.
And then everything else is blocked
Yep.
on a blocking rod that's along the solenoid.
Oh, okay. That's clever.
Yeah, it is. By filtering out all this other stuff,
Yep.
it means that our detectors are only looking at our fused products, and we can
Right.
make them count for a really long time, which
Okay.
means that our precision is a lot better than other labs around the world measuring the same kind of
Right.
reactions.
Right. So how long, when you say count for a long time, hours, days, weeks?
So it'll usually be for tens of minutes or a few hours.
Right. Okay. That is quite a lot. And I
Yeah.
imagine you've got a fair few beam particles coming down and smashing into the target.
Yeah, we have plenty of beam particles.
Right. So lots of data for
There's
you
lots
to
of data.
analyze.
Yeah, that's exactly right. Yeah.
Excellent. Well, good luck with that.
Thank you.